Okay, we are going to work on finding real and complex zeros of a function. So if we were to look at this polynomial right here, you could tell me that, oh, it has a 0 at 2 right here. That's where it's crossing the x-axis. It has one x-intercept, 1, 0 of the graph. That is a real 0 because 2 is a real number. So there may be some complex zeros that exist that involve our friend I, our imaginary number. So if your degree is 3, you can expect there to be 3 total zeros of your function, a combination of real and complex. According to our graph over here, we have one real 0. It appears to be at a positive 2. And I'm going to predict that we're going to be able to find 2 complex zeros, giving us a total of 3 zeros, a combination of real and complex. So first things first, we think that 2 is a 0 of our function, but we do want to confirm this. So x equals 2 appears to be a 0 of the function. We're going to confirm this by plugging it in. Okay, so here I am plugging in x equals 2 for all of the x's of the function. To confirm that you have a 0 from a graph, that's all you have to do. Just plug in a 2 for all the x's because we think it's at a 2. The reason why we want to do that, what if this was a 1.9? And to us, it looks like a 2, but how accurate is it? Like, is it really going through exactly at a 2? So plug it in. When you plug in the value that you think is a 0 of your function, see if you get a 0 back here. If you do, great. We have just confirmed that x equals 2 is a 0 of the function. All right, now, okay, well, oops, the zeros of the function, we just found one of them. We know that one of them is 2. So if x equals 2 is a 0, that means that x minus 2 is a factor of our polynomial. What we're going to do is we are going to divide out an x minus 2 from our polynomial. We could do this with long division, or we could do this with synthetic division. Because what we want to divide by, x minus 2, is just that linear x to the first power, we can go ahead and just do synthetic. It's going to be much faster. So we're going to put a 2 in our little corner box. We're going to write out the coefficients of our polynomial. Check to see if you've skipped any terms and have to fill in a 0, which in this case we don't. So the coefficients of our polynomial are 1, 1, negative 3, negative 6. We're going to start by carrying down our first term. And then remember, we multiply to the corner. 1 times 2 is 2, and write it beneath the next term. Add down. That gives us a 3. Multiply to the corner to get 6. Add down. Multiply to the corner to get 6. Add down, and you get 0. We should get a 0 if this x minus 2 was a factor. So once you get that far, we're going to fill in. Remember, work to the left. This is our constant, which makes this our x to the first power, and this our x squared. So what we have just figured out is that x minus 2 is a factor, and x squared plus 3x plus 3 is a factor. X minus 2 times x squared plus 3x plus 3 gives us our original polynomial. So to find the zeros of the function, we set our factors equal to 0. X minus 2 equals 0. Solve for x equals 2. All right, that's the one we already knew. But here's the one that's going to give us the rest of the zeros of our function. Set the second factor equal to 0. We could try to factor this, but I'll tell you it won't be factorable because if we look back up here at our function, we've already found the only real 0 that we have. It doesn't cross the x-axis anymore, so I'm predicting that we're going to come up with some imaginary solutions. So how do we solve a quadratic equation that we can't factor? How about if we use the quadratic formula? X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Okay, so there's my ABC. A is a 1, B is a 3, C is a 3. So x equals negative 3 plus or minus the square root of b squared minus 4 times a times c all over 2a. We'll simplify this. It's a negative 3 plus or minus. This is, you can just type that into your calculator, but it's 9 minus 12. 9 minus 12, we should get a negative 3 underneath our square root. And there's that square root of a negative. This is why we're about to have an imaginary root. So negative 3 plus or minus, anytime you're square rooting a negative, bring an I out front. Then you can make it positive all over 2. This plus or minus right here is giving us two solutions. So here are our two solutions. It is complex because it involves real parts and imaginary parts. So if we go back to the top and we can add to our list the zeros, we have x equals 2. We have x equals negative 3 plus I root 3 over 2. And we also have x equals negative 3 minus I root 3 over 2. Those are the zeros of the function. This first one is real, and these two are complex. But if you notice, we have 1, 2, 3 total zeros, combining the real and the complex ones, which makes sense when we have a polynomial raised to the third power.